Welcome to our deep dive into the washer method. Today, we are moving beyond simple rotations to find volumes of solids with holes. Specifically, we will focus on rotating regions around shifted horizontal axes, which are lines other than the x-axis. This technique is essential for engineering and physics applications where precision in volume calculation is paramount. When we rotate a region that does not touch the axis of revolution, we create a hole in the center. Think of it like a donut or a pipe. To find the volume, we subtract the volume of the inner empty cylinder from the outer solid cylinder. Understanding this geometry is the key to mastering the washer method. Before we begin, ensure you are comfortable identifying upper and lower functions on a graph. In our examples, we will be working with functions of x, and our integration will occur along the x-axis. Visualizing the area between these curves is the first step in setting up any volume integral. Recall that a volume is simply the accumulation of infinite cross-sectional areas. By integrating the area of a washer from a starting point A to an ending point B, we sum up these thin slices to find the total 3D space occupied by the solid. Precision in setting your limits is vital. The area of a washer is the area of the outer circle minus the area of the inner circle. We express this as pi times the quantity of the outer radius squared minus the inner radius squared. Since our radii change as we move along the x-axis, we define them as functions r of x and r of x. If the axis of revolution y equals k is below the region, the outer radius is the distance from the top function to k, and the inner radius is the distance from the bottom function to k. Subtracting k from our function values effectively shifts our perspective back to a standard calculation. Conversely, if the axis y equals k is above the region, the outer radius is the distance from k down to the furthest function. In this case, the outer function is actually the one with the lower y value. We use k minus the function to keep our radius positive and correct. Putting it all together, the volume equals pi times the integral from a to b of the outer radius squared minus the inner radius squared. Always remember to square the individual radii before subtracting, never subtract the functions and then square the result, as that is a common algebraic error. Let's look at an example. We will rotate the region bounded by y equals x squared and y equals the square root of x around the line y equals -1. First, we identify the intersection points, which are 0 and 1. These will serve as our limits of integration. Now we set up the integral. We have pi times the integral from 0 to 1 of the outer radius squared minus the inner radius squared. Expanding these terms, the ones cancel out, leaving us with a polynomial and a radical term that are straightforward to integrate. After applying the power rule and evaluating at the limits, we find the volume. Plugging in 1 and subtracting the evaluation at 0, we get a final volume of 29 pi over 30 cubic units. This represents the space occupied by the solid generated by that rotation. Now let's try an example where the axis is above the region. We rotate the area between y equals x and y equals x squared around the line y equals 2. In this interval, x is the upper function and x squared is the lower function relative to the x-axis. Setting up our integral from 0 to 1, we square our radii. Notice how the order of subtraction in the radius calculation is crucial for maintaining the correct geometric representation. Even though squaring would mask a sign error, the setup logic must be sound. Simplifying the integrand gives us x to the 4th minus 5x squared plus 4x. Integrating and evaluating from 0 to 1 results in a volume of 8 pi over 15. This process demonstrates that the logic remains consistent regardless of where the axis is placed. What if the axis of revolution passes through the region? This creates a complex solid where parts of the region overlap. In standard calculus problems, we usually assume the axis does not cross the region's interior. If it does, you must split the region into parts that do not cross the axis. It is important to distinguish between horizontal and vertical axes. If we were rotating around a vertical line like x equals h, we would need to rewrite our functions in terms of y and integrate with respect to y. Always match your d variables to the orientation of your axis. A common mistake is swapping the outer and inner radii. This will lead to a negative volume. If you calculate a negative result, go back and check which function is truly further from your axis of revolution. Distance is the key. Another frequent error is subtracting the functions before squaring. Remember, the washer method is the difference of two circles. You must square the outer radius and the inner radius separately before you subtract them. Don't let the algebra trip you up. Always verify your limits of integration. If the bounds aren't given, set the two functions equal to each other to find where they intersect. Using the wrong limits will result in calculating the volume of a completely different solid. To succeed with the washer method, follow this checklist. Start with a clear sketch. Identify your axis and determine if it is above or below the region. Clearly define your outer and inner radii as distances, then set up and evaluate your definite integral carefully. Keep these formulas in your notes. When the axis is below, it's function minus axis. When the axis is above, it's axis minus function. This ensures your radii are always positive values, representing physical distance. Let's test your knowledge. If we rotate the region bounded by y equals x, the x-axis, and x equals 2 around the line y equals -2, what is the outer radius? Think about the distance from the furthest curve to the axis. The correct answer is B, x plus 2. Since the axis y equals -2 is below the region, we take the top function, y equals x, and subtract the axis value, -2. This gives us a distance of x plus 2. You now have the tools to calculate volumes for solids rotated around any horizontal axis. Practice these steps, and you will find that even the most complex shapes can be broken down into simple washers. Mathematics allows us to model the world in 3 dimensions with incredible accuracy. Thank you for joining this lesson on the washer method. Keep practicing, stay curious, and continue exploring the beauty of calculus. This lesson was generated by Vision Solve AI.